Okay, I think it's, after 4 o'clock, so we can start. Hi everyone, welcome back. Hope you all had a nice weekend. Today we're going to be going over pointers, so how we can translate pointer instructions from simple IR to assembly. So before we begin, any questions from last week or anything up till now in the course? Okay, so this was, do you have a question? Or?
I wanted to ask if we wanted to experiment with like the Cogen project locally, is there a with the distribution for Antler 4? I know this might be a weird question, but what is the best method to install that?
Oh, you can just follow the installation instructions on the website. They have installation instructions there. I think you might have to set an alias or something to get it to work in your terminal. I was able to set it up in my Ubuntu machine without too much effort. I know I was able to do that. So, yeah. And you don't have to use C++. Antler has bindings for Python and other languages as well. So if you dislike using C++, you could use another language. In fact, in earlier renditions of the course, we actually had this part of the course being Python, not C++. But we decided to use C++ because it's more similar to C. So, okay, any other questions? All right, so homework 19, I believe this is what we had assigned since last time, correct?
Yes.
All right, so it's a bit of a long one, but you had the whole week to do it. So what you're being asked to do here is write the equivalent x86-64 assembly code for the following function, specifically the branching behavior. So we're going to ignore the function prolog. We'll see what that is in a future lecture. We're just going to basically perform these operations here. We have covered assignments, so I'll be showing this. The homework problem did not ask you to translate the assignment operations, but since we've already covered it in lecture, to make the example more complete, I'll just be going over those as well. Put this on the left, and I'll open up some code here on the right. And now, in order to perform, we'll do the assignment first. A equals 5. What do we need to know about A in order to perform this instruction or translate it to assembly code? Where A is in the stack. So we'll assume for this assignment, as we're writing this code, that will have the following offsets. So we'll say A is at offset -16. It'd be easier if I just put them next to each other like this. B can be at offset -24. And then we have X, we'll say 32. And then Y will be 40. I think I did the math right. So those are all increments of 8 going down. Why are we using negative values?
This stack is built top down.
The stack grows down, yeah. So in address space, the stack grows towards the low address, yes.
I remember saying it, but I forgot exactly how you worded it. You said it's 8 bits.
8 bytes, 8 bytes, because we have 64-bit integers. That's what the 64 and x86 64 stands for, 64-bit integer, 64-bit machine address space. So with 64 bits, we have at our disposal, we make each integer 8 bytes in size. And in a language like C, you have types, so you have variables of different sizes potentially. In our language, to keep things easier for us with implementation, we assume all variables are just 8 bytes in size, 64 bits. Okay, so for A equals 5, what instruction should we use? What's the mnemonic for the operation we should perform to translate this assignment instruction? Move, right? So the letters here are called mnemonics to make it easier for you to remember what the instruction is. So move, what comes first, the source or the destination?
Source.
The source. So how do we specify a number?
$5.
$5. And where are we moving this into?
Negative
negative 16 RBP. So I heard somebody say RAX. I think in the code gen template for the code that we're emitting, we would do RAX first and then go from there into negative 16 RBP. But we're not doing the code gen template here. I'm just translating this as I would, by hand, not necessarily doing what the compiler exactly would. So we'll just translate this directly to this instruction. Yeah.
And you said using like Rx and RBX as intermediaries for safety.
Generality. It just makes it easier for us, again, for the implementation to store our source values in these general purpose registers, the B register and the A register first before going into the destination. It just lets us makes writing the compiler easier. That's all. So the next one we have is going to be B equals 1. That'll be pretty simple, I think. Just changing out the negative 16 for negative 24, changing the 5 out for a 1. Same idea. Now finally we'll do the C equals, or X equals 0. I want to say C because it's the next one alphabetically. 0, negative 32. Okay. Now we have the head label. How do we translate that in assembly? How do we translate a label? Yeah.
Just that.
Yep, it's just the same label. Same syntax. If A is less than or equal to 0, go to a 1. Okay, so how should we translate this? What do we have to do? Yep.
CMP to compare 0 whatever negative 16.
Yes, CMP. And then what comes first? 0, you said 0 comes first, or?
Yeah, 0 comes first.
Yes, that's correct. So 0 would come first, and then we also compare against the variable A. So what would that be here? Negative 16 RBP, because A is at offset negative 16. So we performed the comparison. Now we have to jump to A1 if, what condition? What mnemonic do we use? JLE, jump less than or equal to. So jump less than or equal to A1. So what this apparently or effectively does is check is A less than or equal to 0. That's what this checks. If it is true, then we jump to A. A1, I should say.
Does it matter if it's dollar sign or percent for RBP?
Oh, sorry, that was a typo. Good catch. It should be percent. Yeah, it does matter.
For like register?
Yeah, percent just for specifying the registers. Yeah. Okay, so we probably want to add the A1 label somewhere down here. We'll get to that later, but let's just add it there for now, so our code makes sense. Now inside here, let's go inside the JLE. X equals X plus A. So what should we do first? Let's do this the way the compiler would do it. Let's translate this the way our compiler would translate it, according to what we saw in the previous lecture, previous 2 lectures.
So we would want to load A into RAX.
Okay, so first we want to move A into RAX. Probably would do X first since it's the first operand, but we can do A first, it doesn't matter. Actually, yeah, we can do A first, it doesn't matter. So A is at offset negative 16 RBP, and we said we'll store it in RAX. Then, oops, my 6 key sometimes doesn't want to work. All right, so what is the offset for x? 32, yeah, 32. Put this in our BX so we don't overwrite the A register. Then what instruction do we use for addition? Add. And does it matter what the destination is here, what the order of the operands is? Okay, so what should we put first? RAX, and then RBX. And now how do we put the result back in X? Another move. So it doesn't actually matter the order of the operands here, so long as you move the correct register that has the result in it back into RAX, or back into X in the end. So in this case, where's the result stored? In the B register. So we'll move from the B register to where?
Negative 32 RB.
Yeah, negative 32 RBP. That's where X is. So I'll just clarify here in some comments. Load A into RAX. Load X into RBX. RBX equals RBX plus RAX. And then here we're saying RBX into X. Okay. So I think we've gotten that line done. Here, we'll do next. So same idea. First we'll move the value of A there we go, into the RAX register. Then we'll move the value 1 into the RBX register. And now we're going to perform a sub instruction, and now here the order does matter. Which operand should be on the right? Which one should be on the left? Which one should come first?
The destination on the right and the constant goes on the left.
Okay, so in this case, if the destination, if we're trying to store the result in A, what should we do? I guess it doesn't, well, it doesn't matter actually. If we're trying to store the result of A minus 1, which operand should come first, RAX or RBX?
RBX?
Yes, exactly. So RBX should come first. RBX, RAX, what this essentially will say is RAX equals RAX minus RBX. That's the big idea. Oops. Okay, so now we've done that. The last thing we have to do is move RAX back into the offset at which A is. So we'll say negative 16 RBP again. We have a go to head instruction here. How do we translate that to simple IR, an unconditional jump to assembly? JMP, yeah, JMP head. Then we have our label, already done that. And then finally, x equals x plus b. Again, we'll be moving, we'll say negative 32 RBP into the RAX register. 24, so x is at negative 32, b is at negative 24. So load x into RAX. Need to fix this, it should be b. Load b into RBX. We perform the addition. Order doesn't really matter, same thing as we saw earlier. So RBX, RAX, RBX, and finally we just move the result back into the offset where x is, negative 32. So move RAX into negative 32, RBP, or BP, there we go. Okay, so any questions?
Do we have to write the return attention?
No, you don't have to write return. We haven't covered returns yet, so you don't have to worry about doing the return. Yeah, we're just gonna cover, all we've really covered so far is everything in the middle of the function, so that's all you have to worry about for this one.
Add only works with 2 registers.
Add only works with 2 registers, yeah. Now we can actually check this. There's a website that I think is listed in the course notes. Felix, quote here, assembly. Yeah, this website right here. This person has listed all the x86-64 assembly instructions. Add is on here. And the way to read this is that it tells you the different modes of each instruction. So the first mode, let's see. Let me pick a good example. One of the modes right here, for instance, r/m8 immediate 8 means you can pass either a register or a memory location that is only 8 bits in size. And then the second argument can be an immediate value of only 8 bits in size. So those are all the different modes, all the different combinations of types essentially. So yeah, all these only have a single comma, only 2 arguments at most. So you can only have 2 arguments for the add instruction. Okay, yeah.
So I did this by like adding like just regular numbers to RDX, RDX, and RDX. Is that like fine? I don't have to use this like stack.
No, you don't have to. You don't have to use intermediate variables. You can add values directly to the appropriate registers if you are sure that's correct. For handwritten assignments, anyway. For the compiler, you'll definitely want to generate code using the template. Yeah. So I guess more of a meta question: what is this code on the left actually doing? What is it simulating? Or what kind of construct do we have in C code that we don't have in simple IR? Is this code sort of emulating? A while loop, right? So it's a looping mechanism because we have this head label, presumably that's the top of the loop, and then we have this go-to head at the end going back to the top of the loop. Okay, so I think we can quit this. And any other questions before we continue? All right. So today, we'll be going over pointers. Again, how to translate pointer instructions in simple IR into the corresponding assembly code. Now we're going to be looking at just very simple pointer instructions, but I think just looking at these examples will give you the intuition as to how to translate more complex pointer instructions into assembly code as well. Let's see. So, yeah, there's several different pointer operations we have in simple IR. Here, the first one we're going to be looking at today, there's 3 we're going to be looking at. The first one's going to be reference, so storing the address of a value x into another variable. This is just like in C, the unary prefix operator, ampersand. And I have some this diagram here on the right to sort of help explain this better. So let's say T1 has some address, or T1 is assigned the address of x. Then the way to, I guess, visually represent this is as T1, let me change the color of this line here. Being a pointer to x, essentially. That's what this sort of instruction would do. Make T1 be a pointer to x. And x and T1 have some values we don't care about. That's what these blue hyphens mean. Another operation would be dereference. So in this case, we say on the right-hand side here, T1. If T1 stores an address, in this case T1 does, it stores the value of x. Let's say x has some value 4 in it. Then what this instruction would do, T2 equals asterisk T1, just like in C, it would dereference T1, find the value 4 at the memory address that T1 points to, and then store that value in T2. And finally, dereference assignment. What this would do is go to the address on the left-hand side. So compare this or contrast it to the previous example. The asterisk was on the right-hand side, now it's on the left-hand side. In this case, what we do is dereference the memory address stored on the left-hand side of the assignment, so T1. We go to that address, and we store the value on the right-hand side there. So in this case, we would store 11 at the location where T1 points to, changing the value of x to be 11. So hopefully this is all pretty familiar to you coming from C. We tried to make this very close to how C works. So any questions so far? Okay. So let's see. Yep, all right. So we have a complete example here that I want to walk through on the left. This will be simple IR code. We're assigning some values to this variables x and y, and then we're doing some pointer operations, and then finally returning the value of x. To figure out the answer to this question, what is the value of x that gets returned, I want to step through a more complete example here. And we're not dealing with the stack. Well, we're not working with assembly code here, but I want to represent or show you the program stack because I think it's still useful for this example to understand exactly what's going on in memory. So in this case, what we've done, I've established this arbitrary stack here where we just assume that the base pointer is here at 128, and the first offset for the variable a is going to be at -16. And we're going to execute these instructions one line at a time here on the left. And I'm going to highlight these instructions in red so it's very clear what instruction we're currently working on. So we have the address of each variable, the absolute address, the offset from the base pointer. I'll just put a little label here. RBP is 128. Yeah. Before I begin, can anyone tell me why we have to use offsets for variables and we don't just use absolute addresses? This is maybe a bit trickier of a question, but I'd be impressed if you get it. Yes. So you're getting that's very close to the answer. Basically, yes. We don't know exactly in memory where the base pointer of a stack frame lies. So the operating system is allowed to place this anywhere in the virtual address space, especially with subsequent calls to different functions. The base pointer is going to be placed at different locations all the time. So for us, we need some sort of anchor, I guess, to reference all the variables in regards to. So we use the base pointer as the base of the stack frame, and then we just use negative offsets from that base pointer to get the value addresses of all the variables. Big idea, we don't know the absolute addresses of these variables at runtime, so we have to use these offsets instead. That's why we use offsets. Okay, any questions? All right,
So is it to know where you're at relative to something else?
Yeah. Exactly. We only ever know where we are relative to the base pointer. We don't know the exact address at any time. Yeah. Okay. So first instruction, x equals 8. What we'll do here is just change the value of x to be 8. Next instruction, y equals 9. We'll just change the value of y to be 9. Here's where the first interesting novel instruction appears. T1 equals ampersand x. So if x is here, the ampersand operator will get the address of x. What are we going to store in T1? So -32 is the offset, but what's the address of x? 96. So again, we don't know these exact addresses when our code is running, but just for visualization purposes, you can see what's going on. So storing 96 in T1, because that's the address of x. X is at address 96. And we list the variables below their addresses because, again, the stack grows down. So T1 stores 96. Set this to red so we know which instruction we're now on. T2 will be equal to the result of dereferencing T1. So T1, if T1 is equal to 96, we're going to go to the address 96. Then we're going to get the value at that address. It's going to be x, which is equal to 8. And then we're going to store that value in T2. So T2 should be equal to 8. Can anyone tell me what's going to happen with this last instruction here we first need to do? Okay, yeah, so we first dereference T1. So T1 has 96 in it. So we go to T1, 96 I should say, memory address 96, we find x there, and we change that value to 11. Finally, we have T3 is equal to x, so this is simple. X is equal to 11, we just set T3 to 11. Okay, so any questions? So again, this hopefully gives you a big idea of what we're going to be trying to implement. So now we've seen how the operation works, both at like a conceptual level up here and at more of a lower level memory address representation. And now we're going to see how we can actually emit assembly instructions to make this possible. I think, yeah, this is the next set here. So. Okay, so I think we talked about this already. Yeah, local variables, we need to reference them as relative to the base pointer because we don't know where the stack is at runtime. Not exactly. Before we continue, I think now might be a fine time to take attendance. So let's do that first before we get into the actual details of the different instructions. And I'll stop the recording here for now. Okay, so we'll pick up where we left off. Yeah. And look at getting a reference to a variable, referencing a pointer. So the big idea of how we're going to do this is that we start with the base pointer itself, and then we just add the offset to the base pointer of which the referenced variable lies, and then just store that in the destination variable. So let's see if we can see an example here. All right, so computing following offsets, see the symbol table. What was the next example that I had? All right, yeah. Okay. All right, so I have some examples here. I'll just open those up. So vim reference.s. Okay. So what we're going to do is translate this instruction here, t1 equals ampersand x, into assembly code. So the first thing we need to do, I'll make this bigger and I'll zoom in, is actually get the address of the variable we are referencing. So the address of x is going to be negative 32. So we'll move negative 32 into, oops, wrong one, the RAX register. We'll just move into the A register, store temporarily. Or actually, sorry, got this reversed. This should be RBP. We'll store the base address in RAX. Negative 32 is relevant in the next line. So now what we're going to do is add negative 32 to RAX. So what we've done here, if the x variable lies at offset negative 32, what we've done here is obtain the base pointer's address, the base pointer, the value stored in the base pointer, the address stored in the base pointer, and then we subtract 32 from it, and now we end up with the address of the variable x itself. So I'll go back to the slides here, or the drawing. If the base pointer is 128, and we subtract, let's say, 32 from it, 128 minus 32 is 96, we end up with the address of x itself being stored in RAX. And now that we have the address of x in RAX, we can now just simply move the value in RAX into the T1 variable, so negative 48 RBP. So questions? Now this is a little funny to look at first. We're going to see an example, another diagram soon. I'll step through an example of why this works. But this is the big idea of how to translate these sorts of instructions. These reference instructions, yeah. Good question. I'm glad you asked that. Can anyone think of why we add the negative value instead of just doing sub? Not because it's faster. That's a good guess. It's not because it's faster. Yeah?
Does it have to do with like your bits, you're using a negative versus a positive, you have an extra?
No, not, I think you're talking about like 2's complement. It's not related to that. No. What is in the question or answer?
Could it be because of like integer limits, or like number limits of the number
No, it's not due to numeric limits. No. Good guess, but no. Yeah.
I know in like MIPS there is no sub-immediate, just because they didn't see a reason to or because you can just add a negative number, they just never implemented a way of subtracting an immediate value.
So that might be the case in MIPS, but in x86 we do have access to the sub instruction, so we can subtract values. I guess one thing to look at here is, what is the sign of the offsets in our offset table? It's negative. So it's honestly easier for us in the implementation, again, to just add a negative value because we already have the negative stored directly in the offset table, in the symbol table. Yeesh. Okay. Loud lightning. Yeah, I have friends who visit Florida and they've never been to Florida before and they freak out. They think it's,
sunny.
yeah. They ask, is this normal? Are we in a hurricane? No. All right, so yeah, the reason why we add negative 32, why we add these values, is because it's just simpler in the implementation to just retrieve the negative value immediately and just add that. Rather than in the implementation, what you would have to do is retrieve that offset, negate it to get back to a positive, and then emit a sub instruction, which seems like a lot of work when it's easier just to add the negative. And it will be easier for you reading your compiled code trying to debug it to be able to look at these negative offsets because you're going to be used to the negative offsets for local variables. We're going to be using positive offsets for other things later, and it might be confusing to see both of those. So, but great question. Yeah. Any more? Okay, so what I want to do now, let's see if this is the next slide here. Yep, you can see this is exactly the same thing that I wrote. Now I want to go back to the drawings here, and I'm going to step through the stack one line at a time here. We'll come back to this and see how this works. So let's see where. Oh, actually, I don't have this stored in. This is not. There is no drawing for this one, so sorry. All right, so that's referencing then. I'll have examples for the next set of instructions. But I guess, are we all clear? Yeah, okay. So let's go on to the next one, dereferencing a pointer. So I do have examples for this. So in this case, we're saying some variable is equal to the result of dereferencing a variable on the right-hand side. And again, in simple IR, this is going to be the form. You're not going to have a dereference with an addition or a subtraction or anything. If there is a dereference, it's either there's only one of it appearing on either the left-hand side or the right-hand side. So in this case, dereference on the right-hand side only. Okay, so yeah, what assembly instructions loads a value from an address? Yeah, register indirect move. So we've seen these parentheses before, but before we've been applying an offset to them. but you can actually apply no offset to these parentheses, and what it will essentially do is treat that register as an address and go to the value in memory that address, the register points to at that address, and then retrieve that value. So to demonstrate this, this is where I have my actual illustration now. Let's say we start with some instruction, moving a value 104 into some variable, into the register RAX. So we'll step through this line by line. We don't have any offsets here. We're just concerned with what this instruction here does at the bottom. If we move 104 into RAX, that would change what RAX's value to 104. And now there's two different options here. Let's see what happens if we move RAX into RBX versus moving parenthesized RAX into RBX. So in this case, can anyone tell me what happens? We've seen this a lot of times now, I think, these move instructions. So yeah.
RBX is 104.
Yeah, we just store 104 into RBX. Now let's undo that, and let's pretend that we are instead executing this instruction. In this case, let's assume there are some values in memory here as well. 1, 2, 3, 4, and 5. Can anyone tell me, can anyone guess what's going to happen if we execute this instruction? Yeah.
RBX is going to be 4.
4. So RAX stores the value 104. The parentheses here means to dereference the value first. So we're going to go to the address 104, get the value at that address, which is going to be 4, and then store it in RBX. Yeah.
This is like using the ampersand or like the asterisk.
This is the asterisk. So this is just, I haven't translated the asterisk operation yet. This is just giving you some background into what we're going to be doing to translate the asterisk operation. Yeah. So we don't need to dereference anything to translate the ampersand instructions because we're only getting the address. We're not dereferencing it. For dereference operations, we do need to actually dereference a register. Okay, so hopefully we're all clear on how the parentheses works, how dereferencing works without an offset. So you go to the actual address stored in that register and then get the variable there if there's parentheses around that register. Okay, so back to the example here. Yeah. So T2 equals asterisk T1. The big idea is that we're going to get the value of the dereferenced variable, the address, because the dereferenced variable presumably stores an address. If we're dereferencing T1, it should, we presume, store an address. So we're getting that address. Then we get the value memory at that address using that parentheses operation, that mode we just saw. And then we store the value of the memory at the address that we obtained, or at the result. So wherever T2 is, we store it at the result in T2. Okay, so let's see an example. Let's walk through this. Yeah, T2 equals asterisk T1. So the first thing we have to do is get the value that T1 stores. T1 stores an address. So we want to use a move instruction, and we'll just store it in to RBX. So I'll put a placeholder here, or RAX, I should say. So how do we get the value out of T1? What should we be moving out of? So
-48 RVP.
yes, exactly. So just like any other variable, we're just getting the value out of that variable. T1 just happens to store an address, but an address is really just a number. So we're getting the value out of T1, storing it in RAX. Now we have to get the value out of the place in memory that T1 points to, so we can use that parentheses that we saw earlier to do this. So how can we dereference that address? Sure. We could just do RAX again. Yeah, we're overwriting it, it's fine. But yeah, exactly. Big idea, we just wrap RAX in parentheses. So now we're dereferencing the address that we obtained in the previous instruction. We're getting the value at that address, and now that we have that stored in RAX, how can we store this into T2? What should the destination be?
Negative 56 RB.
Yes, negative 56 RBP, because T2 is at offset negative 56. Yeah.
Would it be sacrilege to combine the first two, like the parentheses around negative 48 REP?
You can't do that in assembly, unfortunately. So you mean like this, like
Yeah.
yeah, you can't do that. You can't have a double dereference. Yeah. So seeing this, do we have any idea, sort of like a conceptual question, how nested pointers might be implemented? We don't have to support nested pointers in simple IR, but how would you think we could implement nested pointers?
Just sort of a repeat of the same function we want to dereference in this case. RAX again.
Yeah, that's why I wrote it again, but yeah. You can just keep dereferencing the same variable. Every time you have an asterisk, we'll put it 2 more times, you can just keep dereferencing it. And that's really, I mean, conceptually, I don't know if compilers will actually implement it this way, but that's basically what they're doing. Just multiple levels of indirection. Okay, yeah.
Would just stacking parentheses work?
You mean here, like this?
Well, like for example, when you had one yeah, like that.
No, again, you can't stack parentheses like that in assembly, unfortunately. It's only one parentheses at a time. Is that what you're asking? Like if we could do that in assembly? Yeah, it's only one layer parentheses at a time.
Do you know the reason for that?
It's probably a hardware reason, probably makes the hardware simpler to implement. And if you can implement multiple layers of indirection with only having one, then why would they have to add support for multiple, you know? Yeah.
Sort of unrelated. In C, what would happen if you tried dereferencing not a pointer? Like just a int?
So just some random address, you mean?
Yeah, like if you just had like int A, and then you try to dereference A, what would happen?
So you'd probably raise a segmentation fault because your program would try and access a region of memory that it does not have permission to access, which is either invalid, has not been allocated, or maybe is reserved for the operating system. This is something you'd learn more about in operating systems course, but essentially memory is virtualized, so the operating system manages for each process what regions of memory it has access to. And if you try to access an arbitrary region of memory, which you don't have access to, the operating system will stop you and probably terminate your process. Yeah.
Is it just convention to store it in a temporary register and then move it to your final destination as opposed to where you do the dereference storing it directly into the negative 56 offset?
Yeah, it's a convention really just for this course we're doing this. So yeah, for this course we do this because it makes it easier to implement the compiler. But an optimizing compiler like GCC or Clang would probably do an optimization like that. And that kind of optimization you just talked about, you just mentioned, is what's known as a peephole optimization. These are like really small optimizations that are easy to perform by just looking at the assembly code first. So like tools like LLVM, which are like compiler tool chains, they optimize code in what's called passes. So they actually read over your compiled assembly code in multiple passes and then perform different optimizations each time. So it's like an iterative approach to making your code faster and faster. And if you're interested in all this, take compilers with Dr. Gazzillo, COP 5621. I think in that course, you build a compiler like in this course, but you also, in recent times that he's taught it, implement some compiler optimizations as well. So, okay, any other questions? We got some good ones so far. Yeah? You're loading the value of, you mean here, correct?
Yeah.
Yeah, you're dereferencing RAX, you're going to the address that RAX stores, and then you're getting the value out of that address. So we're not getting the value of RAX, we're getting the value at the address that RAX stores.
So it's RX is no longer referring to something anymore. It just has the value inside it.
RAX still has a value that associated with it in memory, at wherever, in the RAX register. But we're getting that value, and then we're going to the address in memory in the stack that that value points to, that value indicates, whatever address that the RAX register stores. I can walk through an example here. We have an example that I can walk through to help make it even more clear, I think. Okay, so let's step through this one. Hopefully it'll elucidate things more. So in this case, we're doing T2 equals asterisk T1, what we just saw. We're going to assume the following stack, same as in the first example we saw, or earlier example we saw. We'll start with this instruction and work our way down. So we're going to move negative 48 RBP. So RBP is 128 right here. Negative 48 is at 80. So we're going to move the value at negative 48 RBP into RAX. Let me actually change this to some value, let's say, 6, and we'll say this is 11. Okay. So, again, negative 48 RBP, that's going to be right here. We'll get the value T1, and we'll store it in RAX. This will become 96. Now here we're going to dereference the address that RAX stores. RAX stores 96, so we're going to go to 96. Then we're going to get the value 11, and we're going to store it in RBX. And then finally, we're going to get the value in RBX and put it into negative 56 RBP, which negative 56 is right here, T2. So RBP is 11, RBX is 11, put that into T2, you have 11. All right, so questions? Yeah?
For the first instruction, you got 80 as the address for 96.
Oh, it should be 80. You're right. Sorry. Or no. It should be 80. You're right. Sorry. It should be 80. So we should have gone to 80, which is T1. And then, yeah, it should have been T1. Sorry. Good catch. So it shouldn't have been X. I got a little confused there. I didn't have the numbers laid out ahead of time for this example, so I got a little confused, but yeah, maybe we should do it again, just so it's clear. Yeah, so we go to 48, RBP, goes to RAX. Yeah, so we go to 80 first. Bless you. Move the value here, 11, into RAX.
I think it was right.
No, I think it was right. Yeah, actually, now that I'm stepping through it again, I think it was correct. So, I guess to answer your question, yeah, we had loaded 80 first. So we went to offset 80. We got 96. Then in this instruction, so RAX should be 96. And with this instruction, we dereference 96. So we get the value stored in RAX. We dereference that address. So we go to 96 now. We get the value of X, which I had said was 11. I had erased it, but it was 11. And then we move the value 11 into RBX. And then finally move the value of RBX into negative 56 RBP. That's going to be T2. So this goes here. Yeah. Sorry for the confusion. Hopefully, I don't know. Does anyone still have questions? I realize we kind of backtracked there a few times. Okay. All right, cool. So I'll have to do that again with the next example because I forgot to add values in the stack ahead of time. But we'll get to that when we get to it. Yep, so just what we saw. Okay, so pointer assignment. Let's see. Yeah, this is the last one. So in this case, the asterisk is on the left-hand side. So this is the last of the three pointer operations we're going to be implementing. So now in this case, we're assigning T1 to 11. We're dereferencing T1 and then assigning 11 to the place in memory that T1 points to. Here's the stack frame layout, example here. I don't know why this example is here, but we'll just continue. So, yeah. So we'd seen this before. I'm just going to step through it. This will be pointer assign. So the big idea here is actually the same as we did for the other pointer assign operations where the asterisk was on the right-hand side. Here we're going to be getting the address of the left-hand side first and then assigning into that. So what we first have to do is load the address of the left-hand side into a register. So we'll move -48 RBP into RAX. So now RAX stores the address or the value that T1 stores, which is an address, presumably. Now we're going to dereference that address to get the, let me think, what do we do here again actually? It's RAX. Address. Yeah. We'll move 11 into RBX. This is not something you'll have to do. We'll do it for the sake of just for the compiler. You'll be following this template. So we'll move 11 into RBX first. Yeah, question? Oh, that should be $sign and this should be a %. Yeah, thanks. And I believe, if I'm not mistaken here, what we would do next is simply move our BX into RAX. Yeah, like this. So I think that tracks. So we're getting the address that T1 points to. We're getting the value we're going to be assigning to that address, to the memory location at that address. Then we're moving the new value, 11, into the location that T1 points to. So that location that T1 points to is stored in RAX. We're dereferencing it, getting the address, and putting it into our AX here. I think that's correct, yeah. Let's verify it. Let's look at the slides. So, yeah, this is it. So any questions about how this works? This one's maybe a bit trickier.
I like this more than the arithmetic.
The what?
I like this more than the arithmetic.
Yeah, really? It's a bit more exciting, I'd say, a bit more interesting.
I'd say this before, and that was too confusing.
Oh, really? Interesting. Yeah.
So if you didn't have on the last one, you didn't have parentheses, RAX would just store the address of RBX. The parentheses make it so if you copy over the RBX results into RAX.
Yeah, so if we had this line instead, what would happen?
There's T1 would be pointing to 11 in the memory, which would be like a segment.
Not quite. Not quite.
You just store 11 in RAX.
Yeah, exactly. We would just be moving 11 into RAX. The RAX register would just store 11. So we wouldn't actually be accessing the memory address at all. In fact, we'd be changing, well, yeah, we wouldn't even be accessing the memory address at all. We would just be clobbering whatever was in RAX beforehand, which would be this address. So let's see an example, just another illustration to see how this works. I'll need to put some values in the stack here, so let's just say T1 is equal to, let's do 96 like we had done before. So we'll step through this line by line now, just to see how it works, what's going on in memory. So we go out of negative 48 RBP, that's going to be here. T1, we store that in RAX. So we store 96 in RAX. Then here, we just move the value 11 into RBX. So let's do that here. And finally, the confusing instruction, perhaps, moving RBX into the result of dereferencing RAX. So we're going to be moving 11 into some place in memory. So we're getting the value that RAX stores, 96. We're dereferencing that. So we're going here, where the variable x is, and then we're storing 11 at that address. So any questions? Okay. So again, each of these instructions are like just 3 lines of code. So hopefully it makes it easier for you to follow along, or not follow along, but for you to follow along with the instructions in the compiler or the CodeGen project and just implement these instructions. We'll see the template at the end of these slides, but it's a pretty, I'd say, direct template to follow. Okay, so finally, let's look at a more complete example. Oops. I think we have this here. Yeah, all right. So let's see if I can pull this up in a big slide here. I'm going to copy all this over. Paste this in. All right, and let's try stepping through this. I'm going to delete the prologue code, all this, the assembly code we haven't gone over yet, what it does. I'm just going to delete all this. And I think right here is where we can start. So let me just make sure the code's formatted nicely. Okay. All right, so this, I believe, is the translation of this code we saw in the beginning of the lecture. So in the beginning of the lecture, we stepped through an example of what this is doing at the simple IR level. Now that we've seen all the different pointer operations, I want to actually step through the assembly instructions so we can see what they're doing at the assembly level, how it's affecting the stack. So this is going to be a longer example. This will be the last example we have for today's lecture, just to see everything working together in one long example. Okay, so the first line we have, moving 8 into RAX. So we're going to put 8 here. Moving RAX into negative 32 RBP. So we're going to move the value 8 into negative 32 RBP. That'll be right here. So x becomes 8. Now in the next set of instructions, we move 9 into RAX, so 9 goes here. We move RAX into the address of y, which is negative 40. So y 9 goes into negative 40 RBP. That's going to be right here. And now here we have the first pointer instruction. So this is going to be T1 equals the address of X. So we saw this earlier. First, we're going to move the base pointer itself into RAX. So we're going to store 128 into RAX. Now we're going to add negative 32 to RAX. Why are we adding negative 32? What does that represent?
The offset.
The offset of X. So X is at negative 32, so we add negative 32 to get the address of X. That's what we're doing right here. Then we're moving from RAX into negative 48 RBP. So we're getting the address that we just computed, and we're storing it at negative 48 RBP. That's where T1 is. So we store 96 right here, where T1 is. Okay, now the next instruction is deref T1 to T2. This is going to be T2 is equal to asterisk T1, so I'll just replace this here with that. And I'll actually replace these following comments with their corresponding simple IR code. Okay, so we were on T2 equals T1, I believe. So now we're going to move from negative 48 RBP. So negative 48 RBP stores T1. We're going to get 96. We're going to move it into RAX. I don't have to change anything. RAX already stores 96. Then we'll dereference RAX. So what is this going to do? What does dereferencing with the parentheses do? Okay, so what variable are we going to end up getting the value of? So what? So we're getting at negative 48 RBP, we're storing whatever's there into RAX. At negative 48 RBP is T1. So we've stored 96 into RAX. And here we're dereferencing RAX. So we're treating RAX's value as an address. Yeah?
I was gonna say put 96 into RBX.
Yeah, we put 96 into R. Well, we didn't put, okay, I see what you're saying. No, we're not going to put 96 into RBX. Close. So we're getting 96 and we're doing a dereference of it. So what will that get us the value of? Yeah. Yes, exactly. So we're going to go to the address that 96 points to, 96 is, and we're going to get the variable at that address. So we're going to get the value X. And we're going to store that in RBX. So now, then finally, we're going to move the value in RBX into negative 56 RBP. Why we're using this offset? It's T2, yeah. And that's the instruction we're trying to translate right now. So we're going to get 8 and store it at T2. So that'll be 8. Okay, now for this one, we're going to go to negative 48 RBP again. So again, that's going to be T1. Store their address in 96. The address we find there in 96. The value we find there in 96. So we already had that stored in RAX. So 96 is already in RAX. Then we're going to move 11 into RBX. So put that here. I guess one question, does the order in which we perform these two instructions matter? No, right? So it's just an arbitrary decision, but the order doesn't really matter. And then finally, we're going to move the value in RBX into the dereference of RAX. So where will we be storing? So RBX stores 11. Where are we going to be putting the value 11 at in the stack? In X, right? So X is at address 96. So we're going to address 96. dereferencing what RAX stores, 96, dereferencing that, going to address 96, and we're storing 11 there. And then final set of instructions, these ones should be easy, you've seen these before. We're just getting the value at negative 32 RBP, so that's going to be X, 11. And we're going to assign it to the address negative 64, oops, offset from the base pointer. So we'll go to negative 64. That's going to be right here. And we're going to store 11 in T3. And that's it. Any questions? Okay, last thing I'll leave you with, the coding template. It's in the slides, on the course notes. Look at it, use it as a reference. I think the compiler CodeGen handbook shows you it as well. This is what you can use as a reference for how to translate all the different pointer instructions that we saw today. So reference, dereference, dereference assignment, they all follow this general template here. All right, if you have any more questions, you can ask me afterwards. You come to my office hours, but that'll be it for today. We got done a little early.